Thank you very much. It's been a great day so far, and let me just. I got to tour the cyclotron. Thanks very much, Dan. And I got to tour HEPEC labs. Talked to a lot of interesting stuff. So it's been a pleasure. It's really an honor to be here. So I'm going to describe our work on the NEXO experiment, which is one of the next generation experiments looking for a phenomenon called neutrino double beta decay. And I like to start these talks with this picture. This is, of course, the history of the universe from start to finish. Yeah.
Sorry, do you mind removing the?
Yeah, thank you. Yeah. Okay. Sure. No, I appreciate it. Yes. Is that better? Thank you. So this is a picture of the history of the universe from the Big Bang to the present day. And the reason I start here is that it sort of illustrates why we're so interested in studying fundamental particles, right? The structure at larger scales of the behavior of the universe at the present day is governed by the quantum fluctuations of the interactions of elementary particles very close to the Big Bang. And so we can try and address some of the big unsolved questions in our understanding of cosmology by studying the interactions of those elementary particles. And now I've lost my thing. So one of the big unsolved questions that faces us as physicists is the question that that poses itself when you point a telescope out at the sky. You see lots of galaxies, you see gas, plasma, and stars, but you don't see any antimatter. The universe is full of matter, but no antimatter. We don't see anti-stars, we don't see anti-galaxies. And what that requires is that elementary particles at the beginning of the universe produce an imbalance of matter over antimatter to about 1 part in 10 to the 9. So it's a very small imbalance, but it's required to be there to produce the matter-dominated universe that we see today. And so you can ask the question, okay, where does this asymmetry come from? We've done lots of experiments that measure the interactions of all these particles and different processes and decays and collisions and blah, blah, blah. And we still have not found any interactions that give us the physics that we need to create this asymmetry of matter over antimatter in the universe. So this is an unsolved problem, and we can do particle physics experiments to try and discover the solution. And in particular, one of the places that I think is the most promising to look for the answer to this question is by studying neutrinos. So neutrinos are, other than photons, are the most abundant particles in the universe. They're the uncharged partners to the charged leptons. They're neutral leptons, come in 3 flavors, just like the charged leptons: electron, muon, and tau. But they interact, because they don't have an electric charge, they interact only via the weak force. So they're kind of unique in that sense. And when the standard model of particle physics is sort of originally written down, these particles were assumed to be massless. But they don't quite fit with our current understanding. And that makes them very interesting particles to study. So the first important phenomenon that we've observed with neutrinos is the phenomenon of neutrino oscillations. And this is a property where if you create a beam of neutrinos in a specific flavor state, so if you make a population of neutrinos that are all muon neutrinos, and then allow them to propagate through space, particles will propagate according to quantum states of definite mass. And what you see is that when this beam of muon neutrinos that you start with, at the end of that propagation, it mixes with the other flavor states, and you get some mixture of electron and tau neutrinos in the final state. So this is a quantum mechanical phenomenon. This is sort of, mixing of states that are not simultaneous eigenstates. And what it implies is that you have these 3 states of mass, you have 3 states of flavor, and they're not simultaneous eigenstates, so you have a mixing matrix. But the really crucial thing that this tells you is that these 3 mass states are unique, they're different. So neutrinos must be massive particles. And this, of course, was a major discovery that was rewarded with the 2015 Nobel Prize in Physics. The catch is that we don't know how massive neutrinos are. We've done very impressive, very precise measurements to try and measure the mass of neutrinos, but have come up with numbers that are consistent with 0. And so this is a picture of the Kaplan experiment and which sets the current best limits on the absolute scale of neutrino masses of less than 0.8 eV per c². And when you put this in context with all the other fermions in the standard model, you see something very strange. So we have the quarks, the leptons on this axis of the mass. Our best upper limits on the neutrino masses are way the heck down here. That's a 6th order of magnitude gap in mass between the charged leptons and the neutrinos. So while we know that the Higgs mechanism generates the masses of these particles, this sort of very strange picture begs the question, maybe there's something else going on with neutrinos. So one hypothesis is that neutrinos are what are called Majorana fermions, which just means that there are fewer degrees of freedom that describe the neutrino states. Essentially, neutrinos would be equivalent to their own antiparticles. This is only possible for particles that have no electric charge, because otherwise the charge distinguishes between particles and antiparticles. But it has some very interesting consequences. It would add mass terms to the standard model of Lagrangian that would allow you to create very light neutrino masses without doing any fine-tuning of the coupling of neutrinos to the Higgs boson. So it's sort of a natural way to extend the standard model a little bit to explain the fact that neutrinos are much lighter than other particles. But it would have really profound consequences for particle physics. Majorana fermions would be a fundamentally new kind of elementary particle. You would have mass generated with something other than the Higgs mechanism. You would have equivalence between the particle and antiparticle states. And then very excitingly, Majorana neutrinos would introduce 2 of the key ingredients for creating the matter-antimatter asymmetry that we observe in the universe. It would add additional sources of CP violation, and then crucially, it would introduce interactions that violate conservation of lepton number. So I'll talk a little bit about lepton number conservation, because that's an important concept for the experiments that we do. As far as we know, lepton number is conserved in all standard model processes. So what do I mean by that? What I mean by that is just the number of leptons in the initial state of a reaction is the same as the number of leptons in the final state. Here's an example, beta decay of nuclei. You have a nucleus, one of the neutrons decays into a proton, it emits an electron, which is a lepton, and then an antineutrino, which is an antilepton. So these two things, lepton number cancel out, and you have this lepton number is conserved in this process. What you can do is, this, first of all, this gives you an experimental observable to study, to search for new physics. So if you create a situation where you observe a different number of leptons in the initial states and final states of some interaction, that tells you the lepton number conservation is violated. That would immediately demonstrate the Majorana nature of neutrinos. Neutrinos, this equivalence would introduce physics that violates lepton number. There's a theorem that shows that these two things are required. One requires the other. And then it also, sort of provides new information on physics beyond the standard model. So it's a very interesting thing to look for experimentally. The best tool that we have to do this is studying a process called double beta decay. And this is a nuclear decay process where you have a nucleus, and instead of just undergoing beta decay, it will simultaneously change 2 of the neutrons into 2 protons, and then electrons and antineutrinos. And standard double beta decay, which I denote by 2 neutrino double beta decay, is perfectly allowed within the standard model. We've observed this in several different isotopes. It's a 2nd order process, so it's very rare. The half-life would be measured on the order of 10 to the 18 to 10 to the 21 years. This is, for context, I think the age of the universe is about 10 to the 10 years, so many, many orders of magnitude longer than the age of the universe. But we can see it in experiments. And what we see is we measure the energy of those outgoing electrons. And because they share momentum with the neutrinos, but we don't detect the neutrinos, you get a broad energy spectrum in your experiment, where the endpoint of that spectrum is at what we call the Q value, which is just the mass difference between these 2 nuclei. What we look for when we look for lepton number violation is a different form of this process called neutrinoless double beta, where if neutrinos are Majorana particles, they essentially co-annihilate within the nucleus and never be emitted in the final state. So what you would get is the creation of 2 matter particles without any antimatter particles balancing out. So it violates lepton number by 2 units. We discover this with the immediate evidence of new physics. We demonstrate the Majorana nature of neutrinos. What you look for is because there's no neutrinos emitted to carry away the momentum, all the energy goes to the two electrons. And so you get essentially a delta function signal right at the endpoint of this spectrum. That's the signature that you look for in your experiment. We haven't seen it yet, otherwise this would be a different talk. But our best current limits set limits on the half-life of this process at about 10 to the 26 years. So this is an interesting paper from Professor Kelly and collaborators. You can ask the question, why would we study these very long-lived, very rare nuclear processes? Can't we do this sort of experiment in a collider and look for lepton number annihilation that way? And it turns out that you can directly compare accelerator-based experiments looking for lepton number annihilation to neutrino-less double beta decay experiments in an effective field theory context, where you write down different operators that violate lepton number, and then see how these two experimental constraints constrain the energy scale of those effective operators. And what you find is that basically in every case, in a very general sense, neutrino-less double beta decay at the current level sets much more stringent limits on the energy scale of new physics than other accelerator-based experiments. And there's a very sort of simple reason for this. Avogadro's number is very large. So if you have a macroscopic number of nuclei, you have a lot of initial states that you can look for a lepton number annihilation decay, where it's harder to produce that many initial states in an accelerator-based experiment. So effectively, you have much larger intensity in searches for neutrinos double beta decay, and therefore they're much more stringent probes in physics. How do we interpret the results of these things? This will be important when I tell you some plots of our sensitivity projections. When you look for this peak, you essentially are either measuring or setting a limit on the half-life of this process. That half-life can be translated into constraints on new physics, beyond fundamental physics, through an equation that looks like this, where you have the half-life on the left, that's the thing you measure, a coefficient that represents whatever new physics that produces lepton number annihilation. And then you have two nuclear physics contributions where you have a phase space factor for the electrons coming out, and then a nuclear matrix element which describes a nuclear transition. And in principle, these two things you can calculate. This is very hard to calculate, which is why it's known. You can calculate both of these things from the first principle, and therefore a measurement gives you information on new physics. The most sort of baseline model that we assume when we do these sorts of sensitivity projections is that the decay is driven mainly by the exchange of light neutrino states. In that case, this coefficient takes the form of an effective neutrino mass that we call M beta beta. That allows us to put our experimental limits on a plot to compare them with the allowed parameter space. So that M beta beta parameter, which is parameterizing the new physics, is on the y-axis. On the x-axis is the mass of the lightest neutrino state, which we still don't know. The allowed regions of the parameter space under different assumptions for the neutrino mass ordering are in blue and red, and our experimental constraints on double beta decay come in from the top and make constraints. So the best current limit is the limit in green, which comes from the Cam-Lanzan experiment. Okay, so that's the type of experiment that we're interested in, and hopefully you're convinced that it's a compelling way to search for new physics. So what we're doing now is we're preparing for experiments that will search for this process that will be called the TAMU scale. And I just want to highlight first that this is really a high priority in the nuclear physics community. This is the long-range plan, which is, if you're in high-energy physics, is nuclear physics equivalent to the P5 panel. One of the top recommendations that came out of this process as the highest priority for new experiment construction was the expeditious construction of ton-scale experiments using different isotopes and complementary techniques. So this is really a top priority of the nuclear physics community. And what this means is that what we're trying to do is we're trying to push these constraints farther and explore more of this parameter space and hopefully discover new physics. So where we are right now is we have a series of experiments. Here's a non-exhaustive list of some of the experiments that are trying to look for neutrino double beta decay in a variety of different isotopes. What they have in common is they all have sort of like 10 to 100 kilograms of that isotope. And they all set limits that are on the order of about 10 to the 26 years in terms of that. So what we want to do in the next generation is push another order of magnitude in this sensitivity to this physics parameter. What that requires is another 2 orders of magnitude in sensitivity to the half-life. And to get there, we need to scale up the detectors, we need more isotope, and we also need to lower our backgrounds. So how do you optimize one of these experiments? What drives the sensitivity? Well, I showed you the pictures. We're looking for this delta function signal. There's the 2 neutrino double beta decay. And then in general, there's backgrounds which are dominated by events that come from natural radioactivity in the materials that you use to build the detector. And I like to put this in perspective because this is just a cartoon. This is the sort of biggest thing I could think of on the Texas A&M campus, the football stadium. The biggest in the SEC. If I scale the 2 neutrino double beta decay spectrum to the height of the football stadium, and remember, this is one of the rarest natural processes that we've ever observed. The peak that we're looking for would be less than 1 millimeter tall. So that's the scale of experiment that we're trying to do. So the first thing that you need to do is you just need a lot of the isotope of interest, right? So the more nuclei you have in your experiment, the more likely you are to see one decay before you retire. So that just drives the signal rate up and gives you more sensitivity. The second thing is that you want ultra low backgrounds. You want to push this background spectrum, which is not in real life flat, but just for cartoon. You want to push it down as far as possible. Backgrounds in these experiments are dominated by the natural radioactivity that comes in detector materials. So basically, this is a gigantic campaign of being very careful about how you design the experiments and what materials you use to build it. The third thing is good energy resolution. And this is a little bit, if I sort of flip back and forth, you can see how this might help you. First thing is it concentrates your signal in a narrower region of the parameter space. And the second thing is it allows you to resolve this from the tail of that distribution. The better energy resolution helps you gain a little bit of sensitivity. And then finally, once you've done all of this, the last thing you would like to have is a tool that you can use to reject backgrounds in your analysis. So you want a detector that gives you some capability to distinguish between gamma rays, which at these energies for 2 MeV tend to Compton scatter, giving you multiple interaction points in the detector, discriminating that from double beta decays, where you have 2 lowish energy electrons, and so the interactions in your experiment are sort of point-like and highly localized. So you want some sort of capability to distinguish these 2 to drive the backgrounds down. The TAMU scale program in the US consists of 3 different experiments, each using a different detector technique and a different isotope. I work on Nexo, and I'll tell you a lot about that one. Cupid is an experiment looking for double beta decay in molybdenum 100 using a volumetric detector. And then the Legend program is using high purity germanium crystals, looking for neutrinos double beta decay in germanium 76. And each of these different technologies has different advantages and different disadvantages. And I think having this multi-isotope program going forward will allow us to, if we make a discovery, do very powerful cross-checks and characterize it in physics in a unique way. All right, so I'll talk a little bit about Nexo specifically, which is the experiment that I work on. Nexo is a collaboration of many people from across the world. We have about 200 people currently as collaboration members. The center of mass is really in North America with a lot of institutions from the US and Canada. But we are growing in Europe. We have collaborators in South Africa and a growing number of collaborators in Asia as well. And the idea is that we want to build an experiment at Snow Lab, which is in Northern Ontario, where we use search for neutrinos double beta decay the isotope Xenon-136 using a liquid xenon time projection, which is basically a big cylinder bucket filled with liquid xenon and instrumented with various sensors. The experiment is designed to have about 5 tons of liquid xenon enriched in Xenon-136, so we have a very high efficiency search where we have a lot of isotope in the experiment. And then being at Snow Lab, you bury it deep underground to shield you from backgrounds from cosmic rays. And then an additional shielding, sort of active water detector around the TPC that gives you shielding from radiation in the laboratory environment. Liquid xenon TPC is a nice instrument for doing these sorts of searches. You get a dual channel signal for interactions in the liquid xenon. The liquid xenon is the detector medium as well as the source. You get scintillation light, which propagates out isotropically, you detect with photosensors on the edges of the experiment, and then you get ionized charge, which you can drift up to a collection plane at the top. And by pixelating the collection plane, you get three-dimensional images of each interaction in the TPC with sort of millimeter scale precision. And then, of course, for us, the liquid xenon is the detector medium, so if we enrich it in the isotope of interest, then we have a very high efficiency search for neutrinos double dating. They're also very good at building, we are very good at building low background liquid xenon TPCs. First of all, they're very scalable. We already have ton-scale liquid xenon TPCs operating in the search for dark matter, so we know how to build these detectors at the scale that we need for NEXO. They are very low in background. The xenon itself has no intrinsic backgrounds that would cause a problem for us, and it's very dense when you liquefy it. So the instrumentation, which is all in the outer regions of the detector, where our backgrounds come from, is emitting gamma rays that are stopped in the outer regions of the experiment. So you get your backgrounds get attenuated, and the middle of the experiment is very low in background. You do very high sensitivity search. You can get good energy resolution by combining both the light and the charge signals. And then, of course, the three-dimensional imaging is what gives us this powerful signal and background discrimination, where we can tell if an event interacts twice in the detector as opposed to just point-like interaction. That's characteristic of ours. So when we imagine how we'll do the analysis when we build NEXO, we imagine that it's going to be a multivariate type of analysis. So most of the pictures that I've shown you so far are looking at the energy spectrum, because we're looking for a delta function in energy. So of course, that's one of the key observables that we use in our analysis. In liquid xenon, we use the sum of the light and the charge signals, which gives us the optimal resolution. We also will use the imaging capability. That's what we call the event topology. You'll see this in the ENN. We use neural networks to sort of maximize their sensitivity in terms of the imaging capabilities of the detector. And then the third variable that we use is something we just call standoff distance. And this takes advantage of that attenuation of backgrounds in the outer regions of the detector. This is just the distance of an event from the outer edge of the DC. Backgrounds fall away very steeply, whereas double beta K events are distributed uniformly. And the combination of these three variables gives us our high sensitivity. The first thing that you need to do when you imagine or sort of design an experiment is think about what sort of backgrounds you'll have. We have a data-driven background model for NEXO, where every background, this is a contribution as a fraction of the total background. It's kind of a funny variable. Just think of this as a fraction of our total background. We can split the backgrounds, the expected backgrounds, up into different categories. The key one is intrinsic radioactivity of the detector components. And what we have to do is we have to do an extensive campaign of measuring the radioactivity of everything, every nut and bolt that we think we'll use to build NEXO. And that's what's shown here. Each of these points is a measurement scaled to the amount of material that we think we've used in the experiment. You can see we go down to the level of, you probably can't see it from there, but things like the epoxy, thin layers of epoxy that we want to use to build the sensors have to be measured, characterized, and included in our background model. So we have this background model that comes from measurements of radioactivity in all of our detector components. We run that through a Monte Carlo and use that Monte Carlo to project the sensitivity of the design of the NEXO experiment that we hope to build. And we do that, you can run all of those backgrounds through Monte Carlo and then plot the distribution. So what I'm showing here is the distribution of our projected or simulated data projected onto each of the three variables that we would use in analysis: energy, the topology, and the standoff. The signal that we're looking for is the shaded blue distribution, and then all the other lines are various sources of background. And the key here is that I've projected all of the data onto each of these axes. And if you look at any given variable, you see, obviously, this is hopeless, right? We're totally washed out by background. But the important thing is we don't analyze just the energy. We analyze all of these things in concert. And when we make selection cuts in that three-dimensional space, we can actually get very high sensitivity. So this is the same plot, essentially, now with a toy data set. And with selection cuts, where each of these panels now shows a selection in the high signal noise region on the other two variables. The data set that I'm showing you is simulated with a half-life of 10 to 28 years. And this is a signal that we would discover with 3 sigma sensitivity. Visualizing a three-dimensional analysis is difficult, so we also have this sort of key thing where we try to unravel that three-dimensional parameter space into a one-dimension to make it a little bit more easy to visualize. So that's what this axis is sort of. We take all of the bins in our three-dimensional space and order them by signal to background ratio and plot them along one axis. And what we learned from doing that is that there's two bins here that represent about 600 kilograms of instrumented xenon, where we expect in 10 years less than one background. So we have a background-free region of our experiment that corresponds to about 600 kilograms of enriched xenon. If you plot that in the three-dimensional space, you know, some volume within this with the units analysis space, where these three axes are energy, topology, and the standoff. Outside of this background-free region, we still have detection power, right? You know, this bin, for instance, you could still discover a signal if there was an excess there. But also, the rest of that three-dimensional space allows us to measure our backgrounds in situ. So we can characterize and measure our backgrounds with the same data that we're using to do the physics analysis. And the key here is that if we made a discovery, it would really be robust and unambiguous. There are also two unique features for Nexo that we like to advertise. The first is that if we discover neutrinos double beta decay, we can uniquely sort of perform our own control experiments. So the xenon can be drained from the detector. You can replace it with non-enriched xenon and do the same experiment over. If you don't see a signal, then you know that your original signal is real. Or you can take that enriched xenon and put it into a new detector, maybe a gas detector or something, that you can use in follow-up experiments to more completely characterize. If we don't discover neutrinos double beta, Nexo's technique scales well, and I'll talk a little bit about that at the end of this. So we could build potentially larger versions of this in a way that would give us sensitivity to the next two orders of magnitude. So when we do this full sort of projection of Nexo sensitivity, we find that indeed after 10 years of operation, we get to 10 to the 28 years. Our sensitivity is slightly beyond 10 to the 28 years. And in terms of the physics reach, that would push us about an order of magnitude down below where current experiments are, carving out a lot of allowed parameter space in the inverted hierarchy and also the normal hierarchy where we could potentially discover new physics. The timeline, of course, is important. Right now, Nexo is a concept in our minds. This is the projected timeline that was shown in April of last year. We are here. So right now, we have our CD1 reviews, which is the DOE thing, scheduled for September 2020. And if everything goes great, we expect to be operating in about 2031 and taking our first. Okay, so let me describe quickly a little bit of the R&D that we do in my group, and then I'll talk about other applications in next. So two of the challenges as you scale up these types of experiments are instrumentation and calibrations. This is a picture of the LZ dark matter experiment, which is another big liquid xenon TPC, roughly the same size that we hope to build for next. So it gives you some sense of how big the actual TPC will be. So for charge readout, this is something that we work on quite a bit at SLAC. Nexo charge readout will be at the top of the TPC. We're drifting electrons up to the top. And what we plan to do is have an array of square sensor tiles. We tile that top surface, they collect the charge directly and then read out. Each one of those tiles is then instrumented with cryogenic ASICs that amplify and digitize the signals directly in the liquid xenon and send digital data out. So this is our conceptual design of those modules where we have a sensor tile that collects the electrons and then those signals go to the ASIC and then that goes out of the detector. So at SLAC, the instrumentation division is developing new technologies to do this in a low background and exocompatible way. So the sensing substrate, we plan to use these gold electrodes patterned onto fused silica with connected at the corners so that we have strips in X and Y to get very good position resolution for the millimeter scale. And then the signals are routed around to the back by metallizing the edges of the wafers and then route it into a cryogenic ASIC, which has been developed by again, an instrumentation division. And this is a 32-channel system on chip that amplifies and digitizes the signal. Having it in the xenon reduces the noise, it reduces the amount of material that you need to instrument it, and therefore reduces the backgrounds and improves our energy efficiency. So in our group, on the physics side of things, we're doing a lot of the integration and testing of these sensors. So we're studying the noise performance of the prototype cryo-ASICs in collaboration with the University of San Diego. Now is our postdoc at SLAC. And then testing the integration of these sensors with sensor tiles that can actually be used to collect charging with the xenon. I have a student at one of the local community colleges who's been interning with me to do mechanical testing where we can actually build something that's cryo-compatible. And then our student who's visiting us at SLAC on a DOE fellowship is working with a Stanford group on actually integrating a fully functional charge readout system that can be put into liquid xenon. So here's the first version of that. It just needs to get wire bonded, and then hopefully we'll put it into xenon at the end of about a month from now. The other thing that we work on is calibration techniques. And calibrating big detectors is challenging because by design, the outer regions of the detector attenuate radiation. So what we're developing is radioisotopes that you can basically plumb into the xenon system and inject into the detector, so it'll mix uniformly throughout the liquid volume and give you a nice uniform calibration of the instrument. We've developed a way of producing xenon-127. This is an isotope of xenon, so we know it's going to dissolve in the xenon detector. The key thing that we care about is making it above the energy threshold. So these sorts of dissolved sources are a common technique in liquid xenon detectors, but generally the sources are too low in energy or would create backgrounds in the region of interest for double beta decay. So this is a great source because it does neither of those things. It's above our energy threshold. We get signals about 400 keV, but it's well below the 2.5 MeV-Q value, so it doesn't create backgrounds. And so the idea is that we just continuously inject this isotope into the xenon detector. We have a low activity that allows us to sort of continuously calibrate the instrument during operations without impacting physics data. So we developed this source. We basically proved that we can make it and that we can use it to calibrate xenon TPCs. You make it in a very simple way. You take xenon gas, drop it into a nuclear reactor, you activate the heck out of it, and then xenon-127 is the longest lived product. So you activate it like crazy and then wait a while. You have a very nice source of xenon-127. And then Clark Hardy is a student I worked with at Stanford who did simulation studies proving that this will work for Nexo. And then Jasper is a student at the University of Western Cape that I worked with, analyzing data that we took using the liquid xenon systems at Stanford to prove that we can use this source to calibrate liquid xenon. Okay, so let me grab a sip of water before I go on to the next thing, which is slightly different. Another thing that I've been working on recently is asking the question, okay, we're going to build this very highly specialized low background instrument. What else can we do with it? Can we do other physics besides just searching for neutrinos of the data? And I come from particle astrophysics, so we've been sort of investigating the question of what sort of signals would we see that could be interesting for astrophysics. One of the signatures that we're looking at is charge current reactions on xenon-136. So like a neutrino would come in, interact with the nucleus, essentially undergo an inverse beta decay, create cesium-136 in the final state, and eject an electron. This could be a very interesting new tool for measuring astrophysical neutrinos. It has a very low threshold. Mass difference between xenon and cesium is very low. It's got a relatively high cross-section. And then the key thing is that when this interaction happens, you're left with cesium in an excited state, which then relaxes the ground state by emitting characteristic gamma rays. And so there may be opportunities for tagging the production of cesium. There's no other physical process in a detector like Nexo that produces cesium. So if you can identify that some interaction in your experiment produced cesium, then you can throw away all the backgrounds. You have a sort of background-free measurements of astrophysical neutrinos. So what would you actually detect with this? Well, one thing is solar neutrinos. So solar neutrinos are neutrinos that are produced by fusion processes in the core of the sun. There's a large flux of these neutrinos going through us as we speak. And if you can resolve the energy of those neutrinos, you can actually measure directly the abundance of different fusion processes in the solar fusion chains. And there are experiments that have been doing these measurements typically with electron scattering. And so they get a little bit smeared out, but we do have learned a lot of very interesting things about the solar physics from measuring the solar neutrinos. What this might look like if we were looking at charge current interactions in NEXO is something like this. So it's an absorption range. So you actually produce the full energy of the neutrino minus the theta. So monoenergetic lines of neutrinos like the beryllium-7 and the PEP would show up as lines in your spectrum. And then you would also be able to see populations from the CNO neutrinos, which are a very difficult component that would be of interest for determining the metallicity of the solar core. So we calculate that in an experiment like NEXO, which is not very big on the scale of solar neutrino detectors, you can see about 200 of these beryllium-7 events. What you can do with these events is you can actually look for the shift that you expect in the position of that line from the fact that neutrinos or electrons in the sun are capturing from a continuum and not from bound electron states. That would tell you something about the internal temperature of the sun. And then the CNO neutrinos with these statistics, which are low, but if you do it background free, we could actually have competitive measurements of the CNO flux with dedicated experiments like Borg-CN. Another thing you can look for is exotic models of dark matter, where maybe dark matter interacts through like a charge current-like interaction with the same detector, the same signature in the final state in your detector. The EXO 200 experiment, which was the previous xenon double beta K experiment, looked for this, set world-leading limits. However, if we can actually reduce backgrounds by tagging cesium, NEXO would dramatically improve on this. This is the background limited search, and we can really do a lot better if we use tagging. Okay, so the tagging requires you to understand the nuclear structure of cesium-136. So if you have a neutrino interaction on a xenon-136 nucleus, it will preferentially populate specific excited states. This is the excitation spectrum in that nucleus, and this is the energy. So preferentially populate a 1+ state at about 600 keV, which would then relax through the emission of gamma rays, which is great. The problem is that if you do a calculation of the excited states and predict where these excited states are, nuclear shell models and other calculations actually predict a much richer spectrum of excited states. So the nuclear data that's available right now is really sparse. We don't actually know where all these excited states are, so we can't really model this properly in our experiments. So we got excited about this and started working with nuclear theorists to do these calculations. And one of the key things that we learned from these calculations is actually this lowest line state is predicted to be long-lived. What that would look like in an experiment is that you have your primary interaction when the neutrino interacts, and then sometime later you get the delayed emission of this final gamma ray. And that is a very powerful coincidence signature that you could use to do this tagging. There's nothing else in the experiment that produces this sort of characteristic time signature in your detector. So based on the predictions and based on some back-of-the-envelope calculations, we estimate that this could be used to project backgrounds at the level of about 10 to the 10, essentially meaning that we would indeed have a background-free measurements of these neutrino or dark matter interactions with this.
Does it offer the 590 liners or just the general statement? So you said the 590 kV line, right?
Yeah, so
So
essentially
it's all for hitting that line, or is it just general?
that's right. Well, the key thing is this transition here, the lowest transition. So anything that feeds that transition gives you this signature. But through like sort of spin parity selecting rules, this is the state that's getting populated from those neutrino interactions. Like it's not going to any of these other states. It's preferentially doing this one and not the higher ones.
And that's where the delta T comes from.
The delta T comes from that state going to this 3+, and then the delta T comes from the 3+. Okay, so we got very excited about this. but as experimentalists, we don't trust the nuclear theory calculations. So we need to go measure this. So we did an experimental campaign where we did what are called charge exchange reactions, which are essentially a nuclear reaction where you mimic the neutrino interaction with a proton impinging on a xenon-136 nucleus, creating excited cesium in the final state. And then you put gamma ray detectors around that target and look for the gamma rays that come off of it. So I am not really a nuclear physicist, and the guy that I was working with, Scott, is also not really. We're both sort of liquid xenon people. So we made some friends at Tunnel and at UNCW that do know how to do these measurements really well, and were willing to lend us their time and equipment. Specifically, Calvin Howell was the PI there that really helped us out quite a bit, and Werner and Bill, and then these are various postdocs and staff scientists and students that were actually on the ground with us running these experiments. So we did a few different experiments to try and measure this. You can sort of learning as we go. This is the final configuration that we settled on. We had 7 MeV protons impinging on a xenon-136 gas target. Here's a target, and Tim, a member of UNCW, who actually designed and built the target. And then high-purity germanium detectors surrounding that target chamber to measure gamma rays. This is our spectrum, where we see a lot of new transitions that had never been observed before, coming from the excited states of cesium-136. And then these are 2 spectra where the black is all the data that we have, and then the blue is delayed events in the germanium detectors. So what you can see is you can see lines in this delayed spectrum, meaning that there are indeed long-lived transitions after the interactions.
So are the matching with actually
I don't have the matching. I can. In general, yes. Like we can kind of draw lines between our measurements and the shell model calculations. The energies are all wrong, but not by
the energies are fine. So you can see, but the strengths are matching. Like that's the.
Yeah, roughly. I think it's close enough, and so now we have a much more clear picture of the level structure. Yeah, this was just published at the end of last year. So using the coincidences between those germanium detectors, we were actually able to build from the ground up the level scheme of that nucleus, identifying a bunch of new states. And actually, this was published simultaneously with another paper from the University of Western Cape group that did a nuclear reaction measurement without gamma rays, but also basically confirmed this level structure. And so we published simultaneously, so we're pretty confident in this picture. But the key thing is that within this spectrum, we were able to actually identify 2 long-lived transitions or long-lived states through the time distribution. So this is time after the beam pulse, and this is the number of events, within some narrow energy window around this. And these events, or these delayed signals, are what would give us the tagging capability in an experiment like this. So the implications here is that indeed, we're very excited. There is indeed a new channel to explore for detecting astrophysical neutrinos or dark matter with NEXO. Glenn, our PhD student, is now working on taking these data, plugging them into NEXO simulation, and trying to actually properly calculate the sensitivity that we expect. And then we're preparing for follow-up measurements to more completely map this out, and also up to higher energies, where it might be relevant for supernova neutrino interactions in this. How am I doing on time? 5-10 minutes. Okay, great. All right, so the last thing I want to talk about is going beyond the ton scale. So now I'm going back to neutrinoless double beta decay. And this is sort of like out there. So bear with me. But the natural question is, okay, if we're going to build the next generation of experiments, operate these things over the next 20 years, we're going to reach this sensitivity. What if we want to completely explore this parameter space? What if we want to look for neutrinoless double beta decay all the way down here in the normal hierarchy in this region? What sort of experiment would we need to build? Well, you can do some basic math. You can ask the question, okay, for different isotopes, how much would you need? To reach that sensitivity, you need sensitivity to half-lives on the order of 10 to the 30 years, so another 2 orders of magnitude. And generically, it doesn't matter what isotope you pick, really. If you want one event in a detector per year at that half-life, you need about 300 tons of material. So another 2 orders of magnitude beyond experiments like NEXO. Not only that, but you also need lower backgrounds. So this is a plot showing exposure, which is basically the mass of your detector times the amount of time you operate it, versus your discovery potential in years. So this is the half-life that you'd be able to discover. If your experiment is background free, your discovery potential increases linearly with your exposure. But as soon as you introduce backgrounds, at some point, it starts to roll off and increase instead of linearly, like the square root of the number. And here's the sort of plot of the experiments that are planned for the ton scale. The point here is that you extrapolate any of these out to the 1 kiloton year exposure level. The background levels are not good enough to reach a sensitivity of 10 to the 30 years for any of these technologies. So you not only do you need to scale up the experiment, but you also need lower backgrounds. What's great about liquid xenon TPCs is that as you scale up, you automatically reduce your backgrounds. And that's just due to the self-shielding of liquid xenon. So as you scale up the detector in a linear dimension, your backgrounds in the center of the experiment fall off exponentially. This is a plot showing the attenuation factor as a function of a fraction of the total mass as you sort of cut away the outer regions of the experiments for different masses. So NEXO is on this line. A 300-ton version of NEXO would be on this line. So you get about 2 orders of magnitude suppression of background by not changing anything about NEXO, just building it bigger, filling it with more xenon. And we actually published a paper on this concept with an assortment of people from the liquid xenon community and tried to evaluate how sensitive this could be. It turns out that once you get to this scale, now you're limited, even if you reject all your gamma ray backgrounds, now you're limited by the tail of that 2 neutrino double beta K distribution. So we need to improve our energy resolution a little bit, but not an insane amount. It's not crazy. And indeed, with some basic assumptions about how this detector would operate, we think we can reach a sensitivity of 10 to the 30 years. There's a big fundamental problem with this concept, which is that you cannot buy enough xenon to fill this detector. Yeah. So not only is it too expensive, it would be about $1 billion for a kiloton of xenon. Then you need to enrich it to make it more. But even more important, like there's just not enough xenon available on the market. Like it's highly subsidized. Corrective xenon is highly subsidized because it's a byproduct of oxygen production from the sea industry. And so only about 50 to 100 tons is produced per year. However, if you could somehow pull it out of the atmosphere more cheaply, you could, in principle, get enough xenon. There's plenty of xenon in the atmosphere. Very small component, but if you were able to do it efficiently, you could do it. So now we have R&D programs actually exploring this possibility. Because this is the key technological challenge that we need to overcome to get there. So the Livermore group is leading an effort looking at highly selective and high capacity adsorbent materials that are good at extracting xenon from air. We think, based on some very back of the envelope calculations, we come up with a thermal swing absorption process to do this efficiently, lower the cost of xenon and actually extract it, enough of it to build a xenon detector. So this is ongoing R&D. Our group at SLAC has joined the effort and is starting to collaborate on exploring these materials and trying to design a process that could potentially be efficient enough to do this. And of course, if you could build such an experiment, you're not just doing double beta decay physics. Xenon detectors, low background xenon detectors are great for dark matter searches. You could study neutrino astrophysics, as we discussed. There's a lot of other new, like fundamental physics that you could do with a kiloton scale xenon detector. So, the physics program is broad, and I think we should take seriously the possibility of building these gigantic detectors. And that's the end of my talk. So just to summarize, neutrino double beta decay is driving what we're doing. It's really a powerful probe of new physics. And it's NEXO is well poised to push the next 2 orders of magnitude and hopefully discover the process. We think we could do some exciting astrophysics for free with NEXO based on these new nuclear physics measurements that we did over the last couple of years. And then the technology that we're using is a scalable technology with some admittedly very major challenges. But if we need to go bigger, I think this is the way to do it. So thank you.
Go way back to when you were next, so, especially the event rate, like the energy, those variables. Yeah, these. I know that there's been work in the past from people looking at not new physics contributing to neutrino double beta decay, but new physics modifying the two neutrino double beta decay. Is that something that you guys have in mind, like basically measuring that spectrum precisely enough to cover this energy?
Absolutely,
Way in.
absolutely. Right, so you can look at, you know, new particles being emitted in double beta decay would sort of modify the shape of this gray spectrum. And so that's why we are tracking backgrounds like the potassium 40, which is well below the Q value for neutrino double beta. So that's not really a background for the main physics search, but it does obviously affect our ability to reconstruct the spectrum. So we are making sure we know how much potassium 40 is in the materials we can use. So definitely, I mean, we're not at the level yet, I think, where we're making projections of our sensitivity to those sorts of searches, because we're kind of focused on getting money to build the experiment, but certainly I think that will be part of the physics program.
So your last slide said you have a lot of things to do, so I don't feel too bad asking this, but you know, you're looking at 10, 20, whatever years to cover the whole parameter space. What about Catherine and Project 8? Do you think like they might reach there before you?
So Catherine and Project 8 are, let me find this one. This one, okay.
You're right.
So Catherine and Project 8 on this plot are sort of coming in from this search. They're saying with us on this absolute scale of neutrino density. But this n beta beta parameter is a different combination of the neutrino mass states that is only something that neutrino double beta can. The other thing is that I think we're, depending on how you feel about cosmological measurements of neutrino masses, those measurements are far ahead of the laboratory measurements in terms of their stated sensitivity. So those measurements, you know, CMDS4 or something, could actually tell us where we are on this scale. Experiments like Dune or Juno would tell us which of these two, whether in the blue or the red. So actually, this sort of like convergence of all these different experiments at once is very exciting, because we may have a much different picture of this parameter space in the next 10 to 20 years.
But you're not going to take the long range plan every year till then, right?
Until we get money for it, yeah, man.
So, okay, so I can see that, so the next detector is great, in terms of the sensing the low energy. But how capable is energy?
How high in energy?
Yeah,
do you
yeah.
think
I was wondering whether there's the saturation issue or something.
So, okay, so this is sort of like projections at this point. We think that we could see with the current readout scheme that we're using, we could see like 10 MeV, up to 10 MeV with no saturation at all. And then beyond that, you could correct for saturation. So we're not, again, sort of similar to what Kevin asked, we're not at the level where we're doing these sorts of studies yet, because we're focused really on making sure that we meet our sensitivity goals for neutrinos double beta decay. But certainly that's another sort of physics program that some graduate students will champion and take on in the future. But I suspect we could go up to 10 MeV with some diminishing returns as you get higher because of saturation.
Other questions?
What's your projected like data reading rate? You're going to be seeing from all of that xenon, not just at the edge. Are you closing your window so that you're only looking at the end point of neutrinos double beta, or are you going to be seeing all of the decays, and what kind of data are you?
Yeah, good question. So You know, I don't have the number in like gigabytes per second or anything. We do, you know, what our plan currently is just to stream out continuously. So we have 4,000 channels in the charge and 4,000 channels in the light. We're sampling at 2 megahertz. And I don't have a number for you, unfortunately, but yeah, we definitely want to keep all of this information because this is how we measure our tissue. If the lower energies and sort of in different parts of this parameter space allows us to constrain our background model in the data. So we're not relying on our pre-experiment projections of the values. So we want to keep everything as much as possible.
Good.
I have a question about the slide that we had the non-abundant states.
Yeah, sure.
I don't, you might have explained that, I might have missed it, but we had something below 0 seconds, what was that?
Oh, this, okay. So you're talking about like this stuff down here. This is just like a steady state background. And in 0 is relative to some beam pulse. So there's some backgrounds that are just continuous. And then there's some, you know, you can see sort of funny like structures here from, those are systematics from the germanium detector, like events on the surface are different in time from events in the bulk.
Any question? No? Okay, if not, let's thank the speaker.